So in this session, we will discuss nodal analysis for AC circuits. In the previous sessions, we discussed about nodal analysis for independent voltage source, independent current source, as well as we discussed about nodal analysis for dependent sources for DC networks, for DC circuits. But now we are discussing about AC circuits. Okay. Before discussing this concept, first we will see type of the circuit and the respective impedances. How we are going to take the impedance values for the given circuit. If the circuit is said to be purely resistive, then the that circuit has the impedance Z equal to R. So it is clearly mentioned here. Circuit is said to be purely resistance means R. So hence impedance is represented by Z equal to R. Next category, if the circuit is said to be purely inductive, then the impedance of that inductive circuit is taken as written as Z equal to J omega L, or we can write omega L is nothing but XL, X suffix L. Okay. Next category, if the circuit is said to be purely capacitive. Purely capacitive means then impedance is written as Z equal to minus J divided by omega C. So 1 by omega C is written as X suffix C, XC. Hence Z equal to minus J divided by omega C, or that is equal to minus J XC. Next, if the circuit is of type RL circuit, then the impedance of the circuit is written as Z equal to R plus J omega L. Omega L is nothing but XL. Hence Z equal to R plus XL. If the circuit is said to be RC circuit, then impedance of the circuit is given as Z equal to R minus J divided by omega C. Okay. Simple thing. See, here L is nothing but what? Inductive. Inductive is nothing but J omega L. It is a combination of resistance and inductor is there. Resistance is what? R. Inductor is what? J omega L. Hence it is R plus J omega L. Next category, if this circuit is said to be RC, RC means combination of resistance and capacitance. Resistance is R, capacitance is what? Minus J omega by minus J divided by omega C is there. Hence R minus J omega C. Next, last one, if the circuit is of type series RLC, it is a combination of three elements: resistor, inductor, and capacitor. Resistor is what? R. Inductor is what? J omega L. Capacitor is what? Minus J omega minus J divided by omega C. Combination of these three. Hence we can write R plus J omega L minus J divided by omega C. J omega L is written as JXL. 1 divided by omega C is written as XC. Hence we can simplify this one as R. Let us take J common outside. Omega L is what? XL minus J omega C is written as minus JXC. So J is taken common, left with what? Minus XC. So this is about type of the circuit and respective impedances values. Next we'll take nodal analysis for AC circuits with an example. So see this example. Use the nodal voltage analysis to obtain the current I in the network shown below. So the network is given here. This network has two sources. These two sources are voltage sources, but of type AC. AC voltage sources are there. This is 50 of 0 volt, 50 of 90-degree volt. So if it is so, then how to calculate this what? Current I which is flowing through this branch. Current I is mentioned here. The current I is flowing through this branch. The branch has the value J2. So we have to calculate this current I by using nodal voltage analysis method. So first I will identify how many nodes are present in the given network. So one node and two node. This is ground. This is ground. So first I represented the nodes for the given network. This node is represented by the node V1 and second node is represented by the node V2, and I'm going to represent the currents for these two nodes. So first current I1 is moving away from this node V1 and current I2 is also moving away from this node. Current I3 is moving away from this node. Next coming to second node V2, For V2, current I3 is moving towards, then I represented current I4 is moving away, and one more current, that is current I5 is also moving away. So I represented all the currents for these two nodes. Next step is applying the KCL for these two nodes. Okay. So first apply the KCL, apply the KCL at node V1. Apply the KCL at node V1. So we can write, see here, we can write, so current I1 is moving away, hence I will take minus I1. Okay. Next, current I2 is also moving away, so I will take minus I2. Next, current I3. This is also moving away from the node, so because of that reason, I have also taken this current as a minus I3 is equal to 0. Next step is substitution of all these currents values. The value of current I1. The current I1 is moving from V1 to ground. So through this branch, the current I1 is flowing. Hence, V1. So observe the head of the arrow mark of this current. Arrow mark head is pointing to negative polarity. Hence, we can write V1 minus 50 of 0 degree divided by 5 ohm. See here, minus as it is, V1 minus 50 of 0 degree divided by 5 ohm. Okay. Next take the current, that is current I2 is there, minus as it is. The current I2 is flowing through this branch. So V1 minus 0, V1 minus 0 divided by J2. Okay. Next, minus as it is. The current I3 is flowing through this branch. From V1 to V2 it is flowing. Hence V1 minus V2 divided by 4 is equal to 0. Next, it is further simplification is there. Simplification of these values. I will separate the terms. Minus V1 by 5, minus into minus, plus 50 by 0 is the limit. Minus into minus, 50 by 5. Next, minus V1 divided by J2. Next, 0 is the limit. Next, minus V1 by 4, minus into minus plus V2 by 4 is equal to 0. For the simplification, first I will, how many terms are there for V1? I will observe first. First, 1, 2, 3. There are 3 V1 terms are there. So let us take the V1 common and add the coefficients of V1. Here I have taken the V1 common outside the bracket. Then I am going to write the coefficients of V1 here inside the bracket. For this first term, minus 1 by 5, and the second term minus 1 divided by J2, and this term minus 1 by 4. Next, plus V2 by, I will take V2 outside, nothing but I am going to represent this equation in terms of coefficients of V1 and V2. So in order to calculate by using Cramer's rule or using calculator, I am going to represent the equations in terms of two unknowns, V1 and V2. So V2 multiplied by 1 by 4 is equal to this 50 by 5. It is 10. Plus 10 is there. If you take this plus 10, right side of the equal sign, it becomes minus 10. Okay. Further simplification, even as it is, 1 by 5, that is 0.2, minus 1 by J2, 1 by 4 is 0.25, plus V2, 1 by 4 is 0.25 is equal to minus 10. Hence, next, minus 0.2 minus 0.25. So we can write minus 0.45. So this one, very simple. This value I am simplifying. Okay. Minus 1 divided by J2 is there. Okay. 1 by 2, we can write minus 0.5 divided by J. Already we discussed many times. 1 divided by J. This one we can write minus J. Okay. 1 divided by minus J. This one we can write J. This point you have to remember here. 1 divided by minus 1 divided by J2 is there. 1 by 2 is 0.5. So as I told, 1 divided by minus J, or we can write minus 1 by J is equal to plus J. So same thing is there. Minus 1 divided by J is there. It becomes plus J. 1 by 2 is 0.5, and remaining part is as it is, plus V2 multiplied by 0.25 is equal to minus 10. Okay, I will represent it as equation number 1. Next, similarly apply the KCL for the second node V2. So apply the KCL for the second node V2. Here the second node. For the second node, the current I3 is moving towards. So because of that reason, I will take plus I3, and current I4 is moving away. So it is minus I4. Next, current I5 is moving away. So hence it is minus I5 is equal to 0. Next, substitution of the values. I3 equal to what? It is moving from V1 to V2. Hence V1 minus V2 divided by 4. V1 minus V2 divided by 4. Next, minus as it is the current I4. The current I4 is flowing through this branch. V2 minus 0 divided by minus J2. V2 minus 0 divided by minus J2. Okay. Next current, minus as it is the current I5. The current I5 is moving through this branch. So V2, the head of this current I5 is pointing to negative polarity. Okay. Hence V2 minus 50 of angle 90 degree divided by resistance 2 ohm. So here V2 minus 50 of angle 90 degree divided by 2 is equal to 0. Next step is simplification. V1 by 4 minus V2 by 4, minus of minus it becomes plus V2 by J2, 0 is their limit, minus V2 by 2, minus into minus plus 50 of angle 90 degree divided by 2 is equal to 0. Okay. Next simplification. So I will observe the coefficients of V1 here. I have taken the V1 common here. So if I take V1 common, left with what? 1 by 4. Okay. I'm going to express in terms of two unknowns, V1 and V2. Next, let us see for the V2. Here I have taken the V2 common outside the bracket. Then the coefficients of V2 here minus 1 by 4. Next, the coefficient of here V2 is 1 by J2. Then minus 1 by 2 is equal to 50 by 2, that is 25. Plus 25 is there. If you take this 25 plus 25, right side of the equal sign, it becomes minus 25 of angle 90 degree. For the simplification, V1 1 by 4 is 0.25 plus here minus 1 by 4, it is minus 0.25. 1 by J we can write minus J. 1 by J we can write minus J. Hence uh, it is minus J. 1 by 2 is 0.5 minus 1 by 2, it is 0.5 is equal to minus 25 of angle 90 degree. Next, V1 of it is same, V1 multiplied by 0.25 plus here minus 0.25 minus 0.5. Add these two things, hence it is minus 0.75 minus J 0.5 is equal to minus 25 of angle 90 degree. So this one I represent as a equation number 2. So we got two equations with the two unknowns, V1 and V2. Let us make use of Cramer's rule. First, I will find the determinant of this matrix. I'm going to represent these two equations in terms of matrix format. So in the matrix format means here first the coefficients of first equation. I'm going to write in the matrix for these two equations. Observe the coefficients of V1 and V2 of equation 1. Coefficient of equation V1 is minus 0.45 plus minus 0.45 plus J 0.5 is there. Minus 0.45 plus J 0.5. Next, the coefficient of V2. The coefficient of V2 is 0.25 is there. Okay, it is about equation 1. See, let us go for equation 2. Coefficient of V1, that is 0.25. The coefficient of V2 minus 0.75 minus J 0.5. Constant terms are here. First equation has constant, that is minus 10, and second equation has the constant minus 25 of angle 90 degree. So this indicates I represented equation 1 and equation 2 in matrix form. Let us make use of Cramer's rule in order to find these two unknowns V1 and V2. V1 is calculated by D1 by D. D1 indicates it is the first column elements are replaced by the constant terms will give the first determinant. So V2 equal to D2 by D. D2 is indicates that second column elements are replaced by the constant terms. So in order to calculate V1 and V2, we required D determinant of the matrix D1 and D2. So first I will calculate D determinant of this matrix point minus 0.45 plus j 0.5. Same thing I written here. Next step is multiplication of these two. Here I written minus 0.25 into 0.25, that is minus 0.0625. Okay, for the simplification of this one here, so minus 0.45 into minus 0.75, it is minus into minus plus 0.45 into 0.75, it is 0.3375. Okay, next minus into minus plus plus j 0.45 into 0.5, it is 0.225. Okay, next simplification plus into minus minus j 0.5 into 0.75, it is 0.375. Next step plus into minus minus j into j square j square. So 0.5 multiplied by zero point 0.5, it is 0.25. The remaining part as it is. Same step I written here. Same step I written here. Okay. Next, further simplification. 0.3375. Simplification of these two things. Plus j 0.225 is there. Minus j 0.375 is there. Simplify. You will get minus j 0.15. This is biggest one. This is smallest one. So subtract this one from this. We will get 0.15 because it is plus, it is minus, and we got minus here. Next, j square. J square is minus 1. Minus 1 into minus becomes plus 0.25 as it is. Minus 0.0625. Further simplification, add the real part and imaginary part. So real part is what? 0.3375, 0.25 minus 0.0625 is there. To the simplification, we will get 0.525. This term as it is minus j 0.15. Okay, let us convert. This is in the form of Cartesian, or we can say this is in the form of rectangular form. Let us convert or express this rectangular or Cartesian form in the polar form. Conversion from Cartesian to polar. So already we discussed how to convert in your calculator. If you press make use of method, already we discussed in the previous video, previous class. So if you convert, we will get the answer as 0.5460 of angle minus 15.945. Okay, for calculating I, the current I2 is represented in the branch here. The current I2 is represented in this branch, but thus in the same branch the current is indicated by the problem statement. As per the problem statement I, so we can write I equal to I2. Both are same because both are flowing through the same branch. So for calculating I, nothing but we have to calculate I2, because in the problem statement he is asking for find the current I. So no need of calculation of remaining currents. Directly we have to calculate I2. I2 is nothing but, that is nothing but I. For calculating I equal to I2, only V1 is required. Why V1 is required? Because in this equation we got equation number 1 and equation number 2. We got two unknowns, V1 and V2. Is it necessary to calculate these two unknowns? Not necessary, because as per the problem statement is asking for find the current I. The current I is flowing through this branch. So through this branch means only one current voltage is present, that is V1. So because of that reason, only the value of V1 we have to calculate. So the calculation of V2 is not required. Because of that reason, I am going to calculate D1 first. D1 means the first column elements are replaced by, the first column elements of the matrix are replaced by the constant terms. Minus 10, minus 25 of angle 90 degree,